This is gearbox design. Jose Garcia.
Michael Wolff.
Rodrigo A. Now for our gear design, this is the parameters that we have. We decided that our input and output shaft are going to be rotating on opposite directions. We're going to be transmitting at 2 horsepower, and our rotational speed for the input is 1,120 revolutions per minute, and the output is going to be 70. Now, our application is going to be an electric generator. And these are the conceptual designs that we came up with. This is the first one right here. The second one, which is a planetary gear. We abandoned all of these designs. The first one we abandoned it because we wanted the output shaft and input shaft to be in the same axis. And the second one, because there were way too many calculations and we just had a lot of problems with that. Now here is our process for the gear selection, which we are all very familiar with. And this is how the gear is going to finally look like. We have 2 types of gears. One is going to be 16 teeth, it's going to be made of steel, and then the other one is going to be 64 teeth, it's going to be made of cast iron. And here are our gear results. As you can tell, the tables contain the stress of bending, factor of safety of bending, stress due to wear, and corresponding the factor of safety due to wear. This is the first pinion, first gear, second pinion, second gear, and lastly we have the third pinion dash gear and third gear dash pinion. And as you can see, all of our safety factors are above 1, which is required. And here, these charts come straight from the catalogs. For the 14 teeth we have right here. This is the numbers that we're using. And the 464 teeth, which is the cast iron, is located right here. Now Joe's going to talk about bearing selection.
In order to determine bearing selection, we first need to take into consideration the reaction forces happening at the end of the shaft. So we're going to go there. In this shaft, the reaction forces are shown here and here, and that's for the XY, this is the XZ. So you sum them, and the reaction force on both ends is what the C10 value must take into consideration. This is the same thing for the second shaft, so the same thing happens, and for the third and the final shaft. The C10 calculations goes as follows. You sum your reaction forces. That's the summation depending on which bearing you're using, comes here. This XD is based on desired life, which we used about 26,000 hours. And then the rest are all parameters that are predefined for ball bearings. The A value is 3, and that's how we came up with our C10 values. This is the actual C10 value rating. So what we did was we looked at the bearing that experiences the largest load, which was the 10.9, and we set all the bearings for that, so therefore we can have more uniform bearing application, and it's easier for the gearbox because the holes will all be the same. Now, and also for our one that to support that load, we use a 1640. It has a 0.875 inches bore diameter. And the rest of these values correspond to that chart right there. Mike will now go into the selection of the shaft.
Hello. For the selection of the shaft, we established all of these parameters. We inputted it into an equation that we created in Excel, and what it does is it outputs the minimum diameter that the shaft needs to be to fall within a factor of safety of 1. On right here, these are the input calculations, and these are the programs that we created to output the minimum diameters. This is for the input, the internal shaft 1, internal shaft 2, and output shaft. The internal shaft 2 experienced the largest moment, and therefore needed the largest diameter to fall within the range. So we use this diameter in calculating all the shafts. Using the same shaft diameter, it kept our costs down, so we only had to purchase 1 shaft and cut it into the appropriate lengths. For our cost analysis, you can see here the gears brought almost half of the cost of the entire assembly at close to $600 for the 16 tooth and the 64 tooth combined. There were 6 gears in total. The shafts are around $38. and the ball bearings are 176. The case material that we ended up using was a 6061 aluminum alloy for its strength and weight characteristics. And we also looked at what it would take to machine the shafts and the case to put all the pieces together. In total, we have a total cost of $1,116. And this is our application. It's a windmill electric generator. The input shaft has a 60 revolutions per minute input, and through the step-ups, it goes to a 1,120 output, which powers the generator. And this can be used in residential and commercial applications.
In conclusion, we'd like to state what we would do differently having approached this problem again. What we found was towards the end, when the way we sized our gears, we started from the beginning and worked throughout. As we went through more and more time passed through the gear sets, we found in our second gear set the gears were failing. So we had to go and redo it because of the torque that was transmitted at that point. So if we were to do it again, we would go straight to the point where it experiences the most torque and size the gears accordingly, and then work backwards. And the same thing for the shaft. We found, since we started from the beginning, we found it started failing once again at the second gear set. So we once again started from that point and worked backwards. So knowing what to do now, we would work from the highest point of torque and work backwards to size our shafts to decrease the time spent trying to calculate our gears and our shafts. Thank you.